Hi, I'm Don, and over the past couple of months, I've been trying to make the developer experience for TypeScript devs integrating with mobile money providers easier. I got into more detail about the project I've been working on in a previous video, so if you're interested, take a look at that. The process of creating a good SDK isn't easy and takes up a lot of time, and even after that, there is the issue of trying to document the SDK you built. In one of my previous videos, I mentioned how I love the experience I had integrating with Stripe's SDK, and it's what inspired me to pursue this project. Stripe seems to have found the silver bullet to these issues, and I was fascinated by how they are able to achieve this. So while looking for ideas on how to structure my Node SDK, I decided to dive into Stripe's Node SDK's source code. So I cloned Stripe's Node repo and started going through it. I've been trying to wrap my head around it for a while now, and I've been doing some research on their SDK, and was surprised to learn that their JS SDK was auto-generated. The interesting part is, this wasn't only done for the JS SDK but for all their other SDKs as well. So I was fascinated by this and had been doing some research for about 2 days when I ran into this podcast.
And for the Stripe API, we spit out the open API spec. And then we have this really, really badass tooling that takes the open API spec and generates all 7 of our official supported server languages, like the SDKs for all of those languages. So Ruby, Python, PHP, Node, Go, Java, and .NET. We have Stripe SDKs for all of those languages, and they're all now automatically generated.
I'll share a link to it in the description. So I was fascinated by this and wanted to know as much as I could about this process. The process of auto-generating SDK code starts at the API level, since SDKs are for the most part wrappers around existing APIs. At the API level, developers write very extensive OpenAPI specs for the API. The OpenAPI spec is then taken through an initial SDK generation process, which essentially generates verbose SDK code that isn't really human-friendly. Stripe then has an internal codegen tool that is able to pass the initially generated SDK code into more developer-friendlier code. The next phase comes in the SDKs themselves. Conceptually, I've structured the SDK code into layers. The first part is the type layer that gives us the great developer experience we are used to. It's important to note that this layer does not execute during runtime and is just there for type inference. This layer contains the types that are generated from the OpenAPI specification. For the most part, the SDK code is generic and doesn't declare any specific types. This layer is responsible for introducing types to the Stripe SDK code. The main SDK code has no references to this layer, and this layer only gets added in on import by another project. The functionality of the SDK code exists in the next layer, which is a composition layer that essentially combines all the different Stripe resources as submodules into an object that gets instantiated when you call the constructor on the Stripe class. It's important to note that the Stripe resources don't exist as direct properties of this class, but get introduced later during instantiation when the constructor is called. This means type definitions for the Stripe resources, e.g. accounts or payment intents, don't exist directly within the package. But since the package exported types declare them, they become available to the consumers of the package. This separation of types from the main SDK code isn't new and is usually a result of compiling a TypeScript code into JavaScript while emitting declaration files and other things like source maps. The only difference here is the TypeScript compiler doesn't generate the types from the TypeScript code, since the declarations were already generated by Stripe's codegen tool. The third layer is the resource layer that gets generated by Stripe's codegen tool. And this is the actual translation of the OpenAPI specification into code. The resources defined in the resource layer are what get consumed by the composition layer. The last layer is the utility layer, which is a collection of functions responsible for abstracting away a lot of boilerplate logic. These functions are heavily consumed by the resource layer and the composition layer, and take care of functionality such as making network requests or passing data. While reviewing the code, there are a couple of things that I found interesting. The first was the heavy usage of function prototypes for the second and third layers of the SDK instead of classes, which made really weird and confusing syntax. But after reviewing it for a while, I got the hang of it. Take a look at this function, for example, which is responsible for enabling functions to extend other functions. Another really interesting bit was how there were loading properties on instance initialization, which meant there aren't any type definitions around most of the code within the SDK. So it was really hard to follow where resources were being defined and how the type definitions for those resources were being added. My initial goal while reviewing the Stripe code was to get a better structure for my SDK. However, after about 2 days of reviewing the code, it became clear most of it had been written by a codegen tool, and so I decided against following the project structure. Though it was surprising to learn that most of Stripe's SDK code had been written by code generation tools, it kind of made sense if you think about it, mostly because they have a really big API and it would be tough to maintain both their docs and their SDKs. However, by using a codegen tool, all they need is a great OpenAPI specification, which they can use to generate code for all the different platforms in which they're supported. I'm still working on handling authentication for my SDK, and will probably post some updates on that soon. But until then,